Okay, we're back. So let's talk about how you build a battery. Okay, so as you mentioned, the most reactive metals most easily lose their electrons, and they're at the top of what we call the reactivity series. So if we think about this common sense, right? So we know things on the left side of the periodic table, the metals are very, very reactive. Okay, we've seen these videos online of maybe cesium or sodium or something being thrown into a bucket of water and you get a dramatic reaction. Okay, so that's because they have the lowest electronegativity in effect, right? So reactivity kind of mirrors electronegativity. So these guys have very low electronegativity. They give their electrons away for free, basically. Okay, and then we go down, and as we go down, the metals get more and more stable, if you like, or less and less reactive. So lead, for example, and tin, we see this in everyday use. You know, lead pipes, tin cans back in the day. Copper, we see metallic copper in our houses. Silver, gold, and platinum are used for jewelry. Okay, silver, gold, platinum are used for jewelry because they don't tarnish, they don't react, so they're very unreactive. Okay, so most reactive at the top, least reactive at the bottom. These guys used for jewelry are very unreactive. Okay, they just don't react with anything, so they stay shiny, which is kind of cool. All right, now, so the most reactive metals lose their electrons. They're usually bottom left of the periodic table. Least reactive tend to be kind of more in the middle towards the right. And if you think about the periodic table, that's kind of what we see with the old, what I call the Olympic group, right? So gold, silver, platinum, these guys, palladium, very unreactive. Okay. All right. Now, kind of giving you the answer ahead of time, one of these is the correct balanced redox equation for the Duracell battery, right? So is it copper reacting with zinc ions, that's a zinc plus 2, remember, to make zinc and copper 2 plus, or is it zinc reacts with copper 2 plus to make copper and zinc 2 plus? You can easily figure it out based on reactivity. Okay, so if we look in the table, who's the most reactive? Well, there's zinc and there's copper. Zinc is more reactive than copper, so zinc's going to turn into zinc 2 plus, preferentially, right? Okay, if it was kind of a competition, zinc will be more reactive, it would make zinc plus 2 ions over copper doing it, all right? So we've got to see in one of these processes, which of these processes makes zinc 2 plus. Well, here zinc 2 plus goes to zinc, so it's not that one. Here zinc goes to zinc 2 plus, it is that one, okay? So this, just through inspection and based on position in the reactivity series, zinc is more reactive, it makes plus 2 ions. This is the two correct half equations combined. Okay, now we can kind of flesh that out a little bit, and if you like, we're going to follow through, you know, kind of a bit of a looser, kind of more kind of robust version of the rules, okay? Because these, when we look at these battery half cells, they're very, very simple, and we can kind of just take a couple of shortcuts with the complete rules. So we are going to follow the rules technically, but usually there's not much in the way of hydrogen and oxygen balancing, okay? Oh, pardon me. All right, so let's look here. So write redox equation for the silver nitrate, copper nitrate battery. Okay, now because the counter ion doesn't change, yeah, we can just leave it out, all right? So we have two half equations, yeah? We have two half equations. We've got the copper, and you know, in the book you'll see things written like that, which implies, the silver plus, copper 2 plus half equations, yeah? Okay, we have to figure out who's more reactive. That one will lose electrons, right? Okay, so let's look at it. There's silver and copper are actually next to each other, but copper is more reactive. So copper will go to copper 2 plus 2 electrons. That's our half equation for copper. Okay, what about silver? Well, silver will pick up an electron. Silver plus will pick up an electron to make silver. So it's like the reverse process. Okay, one goes one way, one goes the other. This is, oxidation is loss of electrons. Reduction is gain. Okay, there we go. So those are our two equations, yeah? Nice and easy. If you just want to balance the number of electrons transferred, we're just going to multiply this through by 2. Add them together, what do we get? Nice and easy. Copper plus 2 Ag plus 2 electrons goes to copper 2 plus, 2 electrons plus 2 Ag. Consistent number. Okay, so balancing half equations for batteries is actually pretty straightforward. Just look at where the action is. We could have included the nitrate ion, it would just cancel every time. Okay, so I've done a kind of a simpler version of the rules. Okay, all right, we'll do this in more detail as we go. All right. So, quantification. Now, batteries, of course, we judge how good they are based on their voltage and amperage, mostly voltage, right? Okay, so we buy batteries based on their voltage. And the voltage of a battery is just the difference in electron stealing strength between the two metals. Okay, if they're far apart in terms of their electronegativity, there's a lot of force pushing those electrons from one half cell to another. That's the voltage. Okay, so we're going to quantify the reactivity series with what are called standard potentials or standard voltages. Okay, now this is where it gets a little weird, because while this makes absolute common sense, put the thing that's most reactive at the top, least reactive at the bottom, okay? When we quantify this, instead of oxidation processes, remember, like, you know, we saw these things when they go plus go oxidized, right? We actually look at the reverse process, glass half full, glass half empty. This is why electrochemistry can be confusing. We're actually going to flip this upside down, and we're going to go from the top down again, but this is going to be reduction, okay? So it's going to be the opposite process, all right? So when we look at this next table, it's the same exact order as the reactivity series. It's just switched on its head. So the most reactive metals are at the bottom, the least reactive are at the top, right? Okay, so there's lithium, group 1 plus 1, right? And all that, it's very reactive. There's zinc, you know, come up here, there's copper, there's iron, there's silver, which is very unreactive, okay? All right, and you know, they've got non-metals in there as well. They've thrown a few non-metals in, okay? Now, so quantitative electrochemistry, okay? What we're going to do is have a position for comparison, okay? And, you know, we don't start from the lowest or start from the highest. We kind of pick something in the middle and call it 0. So hydrogen, you know, it can go plus or minus ion. So we say it has 0 strength, if you like. You know, it has 0 strength. And we're going to compare everything to what's called the hydrogen half cell, okay? So there's the hydrogen process, at 2H plus 2 electrons goes to H2. That's the reduction half equation for hydrogen, right? If we compare everything to it, more reactive metals are down here. They have negative numbers. Less reactive metals are up here. They have positive numbers. Remember, we flipped the script. This is reduction, not oxidation, okay? So if you think about it, the strongest reducer is actually fluorine. It's an electron grabber, so that's going to be a big positive number. Lithium is an electron giver, so it's going to be kind of the reverse. When I try and squeeze one on there, it's going to be very negative, right? So it doesn't want to do it, okay? So that's our table of reduction potentials, all right? Now, the voltage of a battery is very, very simple to calculate, and you know, we did it in our lab, nice and easy. It's just the difference between the two numbers, okay? So if you think about, just for a second, think about a Duracell battery. What's the voltage? It's 1.5 volts, right? And it's zinc, copper, right? If I look at zinc and copper in my table here, there's zinc, minus 0.76. There's copper, plus 0.34. If I put those on a number line, and maybe I'll go down here to do it, okay? All you have to do to work out the magnitude of a battery is just put the two potentials, we call them potentials, right? There's 0 if you like, right? Okay, so I've got, it's not a great spot there, plus 0.34, which was our copper, and minus 0.76, which was our zinc. What's the difference between the two? Okay, it's this far, isn't it? Okay, so it's 0.76 to there and then 0.34 to there. Always big number minus small number. We'll look at this in a second. So plus 0.34 minus a minus 0.76 equals 1.1. Now that's not quite the 1.5 volts of a battery, because these are with standard concentrations of 0.1 moles per liter, okay? When you get a battery and you swish it around, you can't listen to the liquid inside it because it's a paste, it's really concentrated. So that pops up to 1.5 with the higher concentration reagents inside, okay? But hey, under standard conditions, it has a voltage of 1.1, okay? So the voltage of a battery, think about a number line. How far is it from here to here? Simple idea. Biggest positive number minus smallest number, okay? So the more positive one minus the more negative one, okay? And that'll always give you that difference between the two. Okay, that's why it's called potential difference, okay? Potential difference is voltage, right? Okay, so working out the magnitude of a battery is very simple. All right, now, the magnitude of a battery, just the difference between the two numbers, all right? However, well, if you had done this lab, and we'd have played some nice little tricks in lab to make sure we actually attached the electrodes in the right positions. You know how sometimes you put the battery in backwards and the thing doesn't work. That's because the flow of electrons is very important. Okay, and you know we have red leads and we have black leads and we have positive terminals and negative terminals, anodes and cathodes and things like that. Okay, now this is where, again, as I've mentioned several times, working out the magnitude is easy. It's just the difference between the two potentials, right? Okay, difference between plus 0.34 and minus 0.76 is 1.1, right? But which is the plus terminal, okay, and which is the minus terminal? So on a battery, you know, one end is plus and one end is minus, okay? Anodes and cathodes, plus and minus terminals, things like that, all right? So how do we work that out? Okay, so how I like to think about this is with the Duracell battery itself, right? Okay, so in a Duracell battery, and maybe, you know, I'll actually draw what one actually looks like down here. This is actually how we do it in the lab. This is how we set it up in the lab. And that is actually mimicking what happens in the real battery. So if you remember, a Duracell battery has a copper colored top, right? That's because the pole that kind of goes down the middle is made of copper, okay? So that part, if I bring it up, right there, where it, you know, attaches to your kind of gear or whatever you're using, that little point there, copper colored top, that's made of copper, right? It's actually copper coated in another metal, but it's copper fundamentally, all right? So copper, if you remember, we're going to have the metal in contact with its ions to make a half cell, right? So in the lab, we would actually make this ourselves, all right? So the copper electrode, we call it, just a slab of copper, it sits in a solution of copper nitrate, okay? In our battery, that would be a paste. So that has copper 2 plus ions in it. There they are. So copper and copper 2 plus are in electrical contact. And then we actually have what's called a porous membrane, usually a kind of a plastic or something. It allows ions to travel to and fro, okay? This is important because ions have to travel in one direction as electrons travel in another. So we have what's called the porous membrane, okay? It's kind of like a plasticky kind of porous material. If you ever seen it on the inside of a battery, don't open one. Okay, all right. So there's our porous membrane. Then we have on the other side the zinc 2 plus system. Okay, as we can see, the zinc 2 plus is there. So the paste is zinc 2 plus. And then believe it or not, the outside layer of a battery, the outside case of a battery is made of zinc. So you can actually touch the lead anywhere on the outer case of the battery. But we normally attach it there, but you can attach it anywhere because it's all zinc, right? Zinc. All right, so that's copper and that's zinc. And then, hey, the electrons will flow around. There's your device, right? There's your iPod or something. All right, there it is. Okay, so that's how we set it up in the lab. All right, so the question is, you know, which is the plus terminal, which is the minus? Now, if you remember a Duracell battery, copper is going to be the plus terminal, right? So this is always a help, yeah? Okay, if you bring a device to the final exam, like a calculator, which happens to have Duracell batteries in it, and you kind of check your batteries during the test, I'll look the other way, okay? Because it's a reminder, right? So here, copper in the copper zinc battery is the plus terminal, zinc is the minus terminal. Now we've got to have a way of remembering that, okay? One of them is going to be assigned the anode, one of them is going to be assigned the cathode. Okay, so electrical conventions can now be used to determine which half cell is assigned the anode and which is the cathode. In other words, the plus or minus sign. Okay, so I like to remember this with vowels, right? Oxidation at the anode. Okay, so oxidation at the anode. So oxidation, oxidation is loss of electrons. The thing that goes plus, right? That's the anode. And reduction at the cathode, all right? So the thing that goes the other way is the cathode. Fair enough. So if you think about it, this is going to be the more reactive metal. What's more reactive, copper or zinc? Well, we just already saw that zinc's more reactive, right? So zinc is going to be the anode, and copper is going to be the cathode. All right. So hey, zinc, copper, oxidation at the anode, more reactive thing. Reduction at the cathode, less reactive thing. But then you've got to remember the sign. Well, copper is the one that's a plus, right? So the cathode is the plus terminal, the anode is the minus terminal. Okay, now that's a convention you just have to somehow remember. And it's kind of tricky, right? So remember, oxidation at the anode, two vowels go together. Oxidation at the anode, oxidation is the more reactive metal of the two. Okay, so that'll be higher in the reactivity series, lower in the reduction series. Okay, then complementary learning, reduction at the other one, reduction at the cathode. But how do you remember the plus and minus thing? Anode is minus, A minus, and cathode, C is plus. Well, it kind of reminds me of high school. This is kind of embarrassing, right? My dream grade was an A minus, because it's England. No one ever gets an A. A minus is your best possible grade. Okay, but what would I normally get on my test? A C plus. Okay, so my actual grade versus my dream grade. Okay, so the cathode is the plus terminal, the anode is the minus terminal. Oxidation at the anode. There we go. All right. So that's how you remember, okay, the definitions. All right, now what they drilled into us in high school, which was kind of silly when I think back in hindsight, okay, how you work out the cell voltage is just the reduction potential of the cathode minus the reduction potential of the anode, right? Okay, so if I look back at my zinc was the anode, all right, so that was 0.76 minus, and copper was the cathode, 0.34. Okay, so they drilled into us in high school. Oh, E cell, E reduction cathode minus E reduction anode, and we have to remember cathode minus anode. But I'm telling you something much simpler. Okay, that's a plus. All right, subtract the more negative number from the plus number and you'll always get a positive answer. Okay, voltages are always positive. If you get a positive voltage, you correctly subtracted them, right? If you always want to get a positive, it's the more plus, subtract the more minus. Okay, if you do it like that, it always works. So this whole business here, you don't really need to know it. The voltages of a cell, the more positive number minus the more negative number, okay? And that is in the table of reduction potentials. So if I look here, so there's my zinc copper, it's this number minus this number. The more positive, plus 0.34, so plus 0.34, net subtract minus 0.76 is really adding 0.76, so it goes positive, 1.1. All right, so hopefully I'm not going too quick here. Bottom line is, when you're constructing batteries, determine the two half cells and then figure out, hey, which one's the anode, which is the cathode. Oxidation at the anode, that's going to be the more reactive one. Anode, negative terminal, A minus, my perfect grade, right? Okay. Insert and evaluate the voltages, or the standard potentials we call them, to get the voltage. So it's the more positive minus the more negative. So for our copper battery, oxidation at the anode, we can write anode there if you want, and that's the negative terminal, minus 0.76. Reduction at the cathode, plus, C plus, A minus, there it is. The difference between those two numbers, just the big minus the small, 1.1. Okay. If you subtracted them correctly, you get the largest possible plus voltage. All right, so what I want you guys to do, and you may want to look online for some of these numbers, okay? Look online for some of these numbers. What I want you to do is work out the, well, let's read the question. Determine the magnitude and sign of the EMF, right? So it's always going to be positive. Okay, if you do the subtraction correctly, it's always going to be positive. Determine the magnitude and sign of the EMF for the following voltaic cells, batteries, okay, constructed from the half cells shown. Okay, so we're going to use these half cells here. You have to kind of split it into two like we did before, define, which one's oxidized, which one's reduced. and here. This is what's called a disproportionation reaction, which we'll get to, okay? But basically a disproportionation reaction means something of an intermediate charge can either go up in charge or down in charge, and if it does both simultaneously, that's called disproportionation. So you can write +2 goes to +3 and +2 goes to 0 charge, two separate reactions, okay, two half reactions. So that's interesting. All right, so give it a pause, come on back. All right. Okay, so welcome back. Let's go through these, okay. So here, the first one's kind of simpler. I've already kind of written it as the two half equations. So if I look back at my reduction potential chart, we're looking at hydrogen and we're looking at copper, right? So copper is higher, right? So copper is higher, so that's the thing that's only going to go reduction, and hydrogen is going to be oxidized. So we're going to flip that one around, okay? So that's going to be oxidation and that's going to be reduction, just based on position in the table, right? And that's kind of what we got, right? So keep this one as it is because it's higher in the series. Reduction, okay, it's adding electrons, all right? It becomes, that's a +2 to a 0. Reduction is gain of electrons, okay? Here, this is a +1 and it goes to a 0. Oxidation is loss, right? Okay, so it actually goes the other way. All right, so those are our two equations. And we're not going to do the whole workup, okay? You know, we'd flip this one and add them, right? But we're not going to do that, okay? We're just going to say, what's the magnitude, okay? So it's always very simple, very simple. It's the more positive minus the less positive. So hopefully that's very obvious. The difference between 0 and plus 0.34 is 0.34, okay? More positive minus more negative, there it is, okay? Down here, we can put the half equations if we want, okay? So fluorine obviously is fluorine is obviously at the top of the scale here, so F2 plus 2 electrons goes to 2F minus. Okay, and if I drew it as it is there, I could, but I'm just going to flip it, right? So H2 goes to 2H plus 2 electrons, and I can just add those two half equations and I get what I want. Okay, fair enough, yeah. But we're not worried about, again, the details of this, we're worried about the magnitudes, right? So this guy here, its potential is plus 2.87. I like to put signs. Hydrogen is 0, right? So the difference between the two is obviously 2.87, but do it correctly, right? So 2.87 plus minus 0 equals 2.87 volts. So when we're comparing to the standard electrode, it's easy, right? It's easy. All right. Now, last one, I got a little tricky. Right? Okay. So here we have a couple of processes. We've got Fe2 plus turns into Fe3 plus an electron. Okay. And then we have Fe2 plus 2 electrons turns into Fe. All right. Oxidation and reduction, right? Now, if we look at the if we balance this all up, we'd have to, do our process. But we're not. We're only interested in magnitude. And the thing with magnitudes of batteries is you don't have to be balancing them, okay? You don't have to worry about how, just because I got twice as many of one type of atom doesn't change the force, right? 2 persons running with the same speed, 10 people running with the same speed, they're running at the same speed, right? So they all have the same voltage. So the number of things does not matter, right? It's the actual identity of the things. So the F2, F plus 2, F plus 3, if we look there, hopefully it's on my list here. There it is, 0.77. So that's 0.77, and that was a plus, right? Plus 2, 0, there, minus 0.45. Okay, so for that battery, or that disproportionation process, okay, it's the plus value minus the smaller value, if you like. Real quick. 0.77, essentially plus 0.54, 1.22. There we go. Okay, so again, working out magnitude is straightforward. Okay, all right. Now, batteries, you buy them, you put them in your phone, whatever device you have, and they provide energy upon demand. So if you think about it, when I press go on my speakers or whatever, any battery-powered device, it works. There's no need for me to warm it up or anything like that, right? So it's spontaneous. So if you think about it, delta G must be minus, okay? So delta G for batteries is always minus, right? And remember, delta G is kind of it's like an energy, right? So delta G is kilojoules per mole, right? So the energy of a battery, delta G, is proportional to its voltage, yeah? And you know this to be true because the more batteries you have in your flashlight, the brighter the flashlight, right? I'll tell you a quick story. Here's a standard flashlight. It may have one battery in it. It's kind of a dim bulb, right? Then you have 3 or 4 of them in there. The voltage is 3 times higher. The brightness is 3 times as much, yeah. Okay, so this is kind of, as I told you, I'll tell you another story about my brother, right? My brother is in nightclub security. He's one of those people that stands outside a nightclub and tells you can't come in. And in England, of course, there's no weapons, right? So, what do they carry just in case it gets rough? They carry a mag light, a big flashlight, right? And your status as a bouncer is defined by how big your flashlight is. I think there's some kind of compensation going on there. That's what I'm saying. But the bigger your mag light, the more powerful it is. And also the heavier it is to smash people with. But anyway, that's just bouncer stuff. All right, now back to it. So E is really EMF or voltage, right? So that's really the voltage of a battery, which is what we've been working out, 1.1 for a copper zinc, for example, right? Okay, and it's proportional, but it's not equal. If I want to make it equal, I have to use this equation right here. Okay, so delta G is the number of electrons transferred. So if it was copper, 2 plus going to copper, it would be 2, right? Okay, so the number of electrons, that consistent number transferred. And if we looked at our first ever redox, that big one, it was 10, right? But normally for batteries, it's 1 or 2, occasionally 3. Okay, so number of electrons transferred. The Faraday constant. Now this relates the mole to basically the electron, okay? So a Faraday is 96,500 coulombs. So a mole of electrons has a Faraday of charge, if that makes sense. Okay, so we're going to always multiply by 96,500 to turn a number into a charge, and then times the voltage. So if you think about it, what is true electrical power? It's voltage times current, right? So power equals VI, right? So that's your voltage and that's your current, and that's your energy right there, okay? So this is all done by Michael Faraday. This is Faraday's equation, right? Okay, so you can work out the delta G for a battery, right? Okay, and because if you think about it, because this is always going to be positive, if we put our leads correct, right? So if we do the big number minus the small number all the time, we always get a positive voltage for a battery. That minus there just turns it into a minus delta G. Remember, minus delta G means spontaneous. All right, now this is all done, of course, by Michael Faraday. Okay, Michael Faraday was famous English electrochemist, kind of the father of electrochemistry, and has the Faraday Constant named after him. He was the first to look at electrochemistry in any detail. Very famous scientist. He was actually on the back of a £20 note for a while in the UK, so that's famous right there, right? Turns out that Margaret Thatcher, of course, is an ex-British Prime Minister, and we used to call her back in the day, when I was in kindergarten, we used to get milk delivered, and when we had our good old socialist government back in the 70s, we used to get free milk as school children. And when Margaret Thatcher came in, she actually was the education minister, her first job, and she actually took the milk away. So we used to call her Maggie Thatcher Milk Snatcher. So, as a 7-year-old kid, she stole my milk. Anyway, later on, she, of course, got promoted, and eventually became the Prime Minister of the UK. And she is actually the only Prime Minister in the UK to hold a degree in chemistry. Okay, so she's dead now, but she had a degree in chemistry. The only English Prime Minister to have a degree in chemistry.